We were studying ring theory and we had decomposed our okay, so we had decomposed our order parameter field into a kind of slow field and a fast field. And okay, remember that this fast field, its Fourier modes lived in some shell of infinitesimal thickness, b lambda, which is sorry, not b, but dl. Okay, d lambda, essentially lambda dl, very thin shell. And what we want to do is to, okay, so this is where these m greater fields live, and we want to derive an effective theory for these slow fields. And so what we'll do is a set of transformations, 3 steps. Okay, so this is what we are going to call a renormalization group transformation. So we want to essentially get rid of these fast modes to obtain a theory only of the slow modes. So the first step is to, okay, I think I'll write it over there, is to integrate out those fast modes. So what that means is that we'll take our partition function, our path integral, and we will only integrate over the fast modes. In case of the Landau-Ginzburg-Wilson functional is a functional of the total m, but we integrate out only this large momentum, large frequency components, and then what we get is something that we will basically take to be, the definition of an effective action for these slow modes. Okay, so that effective action, I'll denote it by S lesser, and it's a functional of the slow modes. Okay, so effective action, the slow modes. And so to do this, we need to sort of expand this to disentangle the contributions to the total action from the slow modes and the fast modes. Okay, we'll do this. If you do this, what you find is that for the quadratic part of the action, then this just splits into a sum of 2 terms. It controlled both by the same functional form for the quadratic piece, and then you get a sum of other terms, okay, which are your interaction terms. So, for example, we had this quartic term here. Okay, so this I'll call the sort of interacting part of the action S int. And the reason that this decouples is so m lesser and m greater decouple at the Gaussian order. Okay, why? So there is, an m less, m greater term, but actually this term vanishes because these are sort of disjoint. They have a disjoint support in the momentum space. In case if you're integrating over dq, quadratic order, this will be something like some kernel f of q, and then let's say m lesser of q, m greater of q. Well, this is 0 because m lesser is 0 for q above lambda over b, and m greater is 0 for q less than lambda over b, so they don't overlap. So this is 0. So this effective action for the slow fields obtained by integrating out the fast fields will have 2 types of contributions. One of them will be simply the Gaussian piece, which is just the same as for the full theory. This just factors out. But then there will be something non-trivial obtained by integrating over the m lesser of this sort of coupled term. Okay, so this this term gives us just something that sits in the effective action. This piece, we integrate over it as just a constant. It's the partition function that I'll call z naught greater of the free fast modes. Okay, this is just integral over the m greater of e to the minus s naught of m greater, just some Gaussian partition function. So it will just be a constant contribution to the effective action. We'll ignore it. And then there will be an average over the fast fields of this interaction piece. So e to the minus s int, and this is average over the fast fields. Okay, so I define this fast average to be, okay, this doesn't move. So this is, the fast average is defined to be, 1 over z naught greater of integral of bm greater of this interaction piece. Okay, so with the fast action sort of Boltzmann weight, and then average over, whatever average of whatever quantity I want to compute here, this Boltzmann weight from the interaction terms. So, okay, so the difficult part of the computation, of course, is to try to calculate this and see what we get. So, okay, so so without doing an explicit computation, what do we expect to get? So we will get some terms that, as we'll see, if we do this with this infinitesimal shell, what we'll get is an effective action that has the same form as the original action, but with different couplings. Okay, and also we'll generate more couplings, but if we were to consider the set of all possible couplings, then same terms. Okay, but the action will look the same but with a different couplings and also different cutoff. Okay, so what we'll get is like S lesser of n less. Okay, so because we've now writing back in real space, because we've integrated out modes with momenta greater than lambda over b, then now our cutoff is different. So in real space, the sort of effective lattice spacing has increased by a factor of b, or sort of mesoscopic region size, and then we'll get, for example, we'll get a kinetic term for these slow fields, but with a coupling that has changed by an amount delta k. Likewise for other terms, for example, this quadratic piece, this mass term, m less greater, the interaction term. Okay, and all these corrections, they're all going to be, all right, where d lambda, I guess I'll call this delta lambda. So if lambda is any of these couplings, then this sort of change of the coupling will be proportional to dl, the width of our shell. Okay, where this coupling here is any of these three couplings here, k, r, u, and however many couplings we have in our interaction. All right, so that's the first step. So to integrate out the fast fields, and then what do we do? So we're going to rescale. Okay, so what that means is that to try to compare the two theories, the initial theory and the theory for the slow modes, we want to compare them, so they need to be comparable, so they need to have the same cutoff. Okay, so again, the idea is to, if we're at a quantum critical point, then we have scale invariance, and so the effective action should be the same, but that's only sensible if the cutoff hasn't changed. So to compare with the original theory with cutoff, or if you will, it's like a pixel size if you want, lambda inverse, then we need to rescale the coordinates. Okay, so we'll rescale x to x prime will be x over b. So that means the derivatives will be replaced by derivatives with respect to this x prime, so they'll pick up a factor of b. So if we write this action for the rescaled coordinates in the rescaled system of coordinates, we'll get the following. Okay, so we'll get S lesser of M lesser is integral over X prime with now the same cutoff we started with, integrating over dx prime, but now there's various factors of b that show up. So for the gradient term, we have b minus 2 partial mu prime squared r plus dr bd m lesser squared 1 over 4 old u plus delta u b to the d m lesser the fourth and so on. Okay, so at this step, so in this case, because we have the Lorentz invariant theory with dynamic exponents equals 1, we're going to rescale, all the space-time coordinates in the same way. If you had a theory with a different scaling, a non-relativistic theory, then you would, scale x and t with different exponents in general. Okay, so this is where the z would come in. In this case, the simpler case, we know that z is 1, so we don't need to rescale space and time differently. Okay, so that's the second step, very simple step. And then finally, to bring the theory back into the original form, we want to enforce the fact that at the scale invariant quantum critical point, then the two actions are exactly the same. So I'll call this step renormalize. We rescaled the coordinates, but also renormalize the fields. So at the scale invariant quantum phase transition, so the new and all actions should coincide. So what we'll do is we'll define a renormalized field. Okay, so I'll define the field M prime of X prime to be B to D minus 2 plus eta over 2 of M lesser of X. Okay, so here it's Bx prime expressed in the X prime system of coordinates. And the idea will be to rescale things such that this first term looks like a just like the original term, it would be a different coupling. So the first term, A plus delta K, B d to the minus 2, over there, partial mu prime of M less squared. So we demand that this be equal to some K prime over 2 partial mu prime M prime. Okay, everything is primed. So this K prime is a renormalized coupling. So we can find the relation between the renormalized coupling and the original one. Okay, so using this relation between M prime and M less, we got B to the minus eta, K plus delta K. Okay, so remember that B is 1 plus DL, where DL is some infinitesimal. So I expand everything to leading order in the thickness of that shell in the DL. So, and likewise, I'll pull out a factor of K. So I get K 1 minus eta at DL, and then I get 1 plus, okay, pulled out a factor of K, and then this delta K, I'll write it as delta K over DL times DL. Okay, so I again expand this to a linear order in DL. I get K 1 plus 1 over K, delta K over DL. So remember that, delta K, I said this was going to be of order DL, so this will be a quantity of order 1 times DL minus eta DL. And then in terms of order DL squared, which we ignore. And okay, so the idea is that we want to define our renormalized field M prime that was over here, okay, in such a way that this kinetic term does not change. Okay, so that's a choice we can make. It's a freedom we have in the theory. Can choose K prime to remain unchanged under the scaling transformations by choosing this is sort of free parameter eta that I introduced in the definition of M prime to be 1 over k delta k over dl. Okay, so this quantity, as we'll see, this is actually the anomalous dimension of the order parameter. Okay, so this will enter the power law in the 2-point function of the order parameter field is the difference between the dimension of that operator at the critical point and that in the free theory. Okay, so that was for this k prime, but once we've done that, in general, the other terms will, the other couplings will not remain invariant, they will flow, but we can determine how they flow again by writing what these prime couplings will be. Okay, so if I plug in this M prime instead of M lesser, and what I get for the second and third terms, so the M squared and the M to the fourth, you can write the action again in terms of these prime couplings. So R prime will be B, the 2 minus eta, R plus delta R. So this is, R plus delta R. Again, B is 1 plus DL, so this is 1 plus 2 minus eta DL. So I can derive a differential equation for the flow of these couplings. Okay, so kind of dr over dl, really sort of R prime minus R, the amount by which the coupling has changed under renormalization, divided by the thickness of the shell. Okay, so this, so when we'll write dr over dl, this is the rate of change of this coupling. That's really, really what this means in this framework is the left-hand side. Using this same method, we derive that the rate of change is 2 minus eta plus something I'll call eta 2 r. Eta 2 is just like this eta was computed from the amount by which the coefficient of the kinetic term changes. Here eta 2 is defined by, comes from the amount by which this mass term changes. So delta R over dl. Okay, and so this flow equation, the right-hand side, we typically call this a beta function. So this will be the beta function for coupling R, which is a function of all the couplings in the theory in general. So here R and U. And then finally, we have a similar flow equation for the Quartet coupling. Okay, so we have U prime is B to the 4 minus D minus 2 eta U plus delta U. So it's U plus delta U 1 plus 4 minus D minus 2 eta dl. And so U prime minus U over dl, which is what I'll call du dl, is epsilon minus 2 eta plus what I'll call eta 4 u. Okay, where again eta 4 comes from the rate of change of the U coupling obtained from integrating out the slow fields, the fast fields, and then epsilon is just defined to be 4 minus d. Okay, which is 3 minus the spatial dimension, which is the distance from the upper critical dimension. Okay, so greater than 0 in this regime where we need to look at fluctuations carefully, which is below the upper critical dimension. And again, this right-hand side is what we'll call the beta function for this U coupling, which is a function of R and U as well. Okay, so these are called the flow equations or renormalization group equations. Okay, so maybe this one I'll call it 1, and this one 2 to describe these renormalized couplings. So R of L. So now I think of these as functions of this flow parameter L. Okay, so now I think of this not just as some infinitesimal, but some continuous variable that is increasing as we go towards the infrared. So we look at how these couplings flow under a change of scale, of coarse graining scale. All right, so this describes the flow of these couplings. Again, how can we use these to determine critical properties, which is our goal? Well, remember I told you that the assumption here is that at a critical point, there is no length scale. And so the effective theory should be invariant under changes of scale. And therefore, we want to find solutions of these equations that are fixed point solutions. Okay, so basically where this rate of change of the coupling goes to 0. So quantum phase transitions will correspond to scale invariant fixed points. So a quantum phase transition is a scale invariant fixed point, which is a common 0 of those two-bit functions. So, you know, at such a fixed point, those couplings acquire a specific value that, you know, doesn't change under further change of scale of these so-called beta functions. We find zeros of the right-hand side of these equations, then the couplings don't flow. Okay, right. So this implies du dl, dr dl is they're both 0 at such a fixed point if such a fixed point exists. All right, so that's the basic idea. Now, suppose we find such a fixed point. How does that help us compute critical exponents? Okay, so from these, we can calculate critical exponents. Okay, for example, so I told you that this eta was the anomalous dimension of the field. So I didn't really show that. I just said that. How can we see this? Well, we can actually compute this two-point function that I called chi earlier, function of okay, so for example, this will be computing the yeah, I suppose I can do it like that. Doesn't matter that much. Okay. Right, so as a function of the space-time position, and here I'll keep this mass parameter r. So it's just a correlation function, just a path integral over you know, these two insertions. Okay, and the idea is that I want to compute this. Of course, I will only see the universal power law behavior for distances that are much bigger than the coarse graining scale. So for x, much bigger than lambda inverse. Okay. And so since the partition function doesn't change, the actual partition function itself does not change under the coarse graining, then 1 over z is the same as 1 over z prime. And then okay, so then we want to we'll replace this integral by an integral over the slow fields, okay, because we're interested only in computing the partition function, rather this correlation function in this sort of long distance limit. And so these, you know, these fields here really are the same as m lesser. We can replace these by m lesser, and therefore get my path integral here and write it as this integral here, this theory here. So okay, after I basically integrated out, right? So I do the path integral over m greater. I'm left with this effective action for the slow fields. Okay, so the same idea, but now I have an insertion. Okay, and then here I can replace these by m lesser of x, m lesser of 0. Again, I do my this was sort of, you know, the first step, integrate out fast fields. Then I, you know, rescale the coordinate, renormalize the field, So we do that simultaneously. And I get 1 over z prime integral over dm prime e to the minus okay s, which is integral over this effective action with the original cutoff s prime m prime. But now I have this insertion, okay, this factor from the definition of the renormalized field. So I have b to the minus d minus 2 plus eta over 2, but there's 2 fields, so there's no 1/2 here, and then m prime of x over b prime of 0. It's x prime, but x prime is x over b. Okay, but this is nothing but I pull out this factor b to the minus d minus 2 plus eta. Okay, but this is just the path integral representation of exactly the same relation function, but at x over b. And also r prime, you know, with a new coupling r prime instead of r, okay, which is b to some power that I'll call y. And you know, from our previous derivations, this power is 2 minus eta plus eta 2. Okay, so I've derived, you know, a relation between chi of x and r and chi at a difference that are rescaled x divided by b instead of x. Okay, and then this is sort of general. And then the final step is to say that, and is to impose that we are at a fixed point where r prime is equal to r. Okay, so r prime doesn't change if we're at a fixed point. And so if r prime is in fact equal to r, and we're at a fixed point r star, then what we've shown is that you know, omitting the dependence on this r, which is now the same on both sides of the equation, we have you know, the correlation function at the fixed point of x is b minus d minus 2 plus eta I star of x over b. Okay, so this clearly the solution of this is a homogeneous function. The power law, in other words, chi star of x goes like 1 over x to the d minus 2 plus eta. Okay, so we recognize that clearly eta is defined in the usual way as the anomalous dimension of that field. All right, so that was for that would give us this anomalous dimension. To get a complete set of exponents, we would need, for example, the correlation length exponent. So again, how can we get that from those various quantities we've defined? Well, then we just need to move slightly away from criticality. So if we say that r is not equal to r star, it's not a fixed point. Okay, so I have this more general equation that I write, but you know, chi of x and r equals to this at a different x and a different r, but this b here is arbitrary. So I can choose b, clever way. So if I choose b to be r to the minus 1 over y sub r, then the equation that I've derived just tells me that chi of x at, you know, with this mass parameter r is r to the d minus 2 plus eta over y sub r, and that equals chi at r to the 1 over y sub r times x and then 1. Okay, because I've chosen this b in such a way that r prime is this 1. Okay, and then but finally we know that you know, if we're at the critical point, there's no length scale. If we are slightly away from the critical point, then as far as these sort of long range correlations are concerned, these long distance correlations are concerned, there's only one length scale in the problem, which is c itself, and therefore the dependence on x of the correlation function should be via this dimensionless ratio of x over c. Okay, so therefore this means that, you know, this thing here needs to be essentially 1 over c, and therefore I'll just write it here maybe. Okay, so c must go like r to the minus 1 over y sub r, and therefore from there nu is 1 over y sub r is 1 over 2 minus eta plus eta 2. Okay, so if we can compute eta and eta 2, and we find a fixed point, then we know all the critical, well, the standard critical exponents. Again, one could also compute dimensions of other operators beyond, these few data. Yeah, but these are the usual thermodynamic exponents. We'll say all. All right, so this is kind of general, but suppose we're really interested in this Ising model. So how do we go about in practice to compute these exponents? And so I'll just sort of sketch the calculation. There's a bunch of details, but I'll give enough to hopefully convince you that yes, we do find a critical point, and it describes the 3D Ising model. Okay, so to obtain, so basically we need to actually compute these beta functions, and so that means we must calculate these unknown shifts in the coupling constants from which we could obtain these anomalous dimensions eta, eta 2, eta 4, which again are obtained from these changes delta k, change in the stiffness or kinetic term coefficient of the mass term delta r, and of the Quartet coupling delta u. All right, so recall that. Okay, so this was the first step, integrating out the fast fields, and so when we did that, we got a formal expression for this effective action, from which we will be able to read off these shifts in the coupling constant. There's a free part, and then there's a constant piece, which will come from the log of this sort of free partition function of the fast fields. This just a constant, we'll ignore that. And then there's the log of this average of the interacting part. Okay, so this is kind of where all the non-trivial physics occurs. So we can first look at a very simple case where there's no Quartet coupling. The theory is entirely free. What do we get in this case? So if we just set u to 0 in our original theory, which is the Gaussian limit, then right, nothing happens, right? So this is 0. These couplings in the quadratic piece, they're the same, okay, because we just get S naught. So there's no shift, and there's clearly no attracting term either. So all these shifts are 0. Therefore, all these anomalous dimensions, eta, eta 2, eta 4, which is not surprising because we demanded, this free theory to be, essentially a fixed point. More precisely, there's a beta function for this R coupling. Okay, so there's a d minus 2 piece there, or just a 2 here. There's 2 minus eta plus eta 2 times R. Eta 2 are 0, so we still have the 2. And for the beta function for the Quartet coupling, again, all the etas are 0. We just get epsilon u. So if we look for a fixed point, well, there's one fixed point, only one, which is both coupling 0. Okay, so this is what we call a Gaussian fixed point. It's a free massless scalar field. So it's a fixed point, but it's an unstable fixed point, and it's unstable in 2 directions in the space of couplings. Okay, so pictorially, if you were to plot the flow trajectories that you get from integrating those equations in the space of R and U, then we have this Gaussian fixed point here, and then any small perturbation, any small admixture of U and R will take you away from that fixed point in all these directions. Okay, So what's the meaning of some of these fixed points? Well, for example, if we said u equals 0, then there's a fixed point at, there's another fixed point, if you will, at infinite r. That is not a critical point. This is a phase. So this is really the symmetric phase. It tells you the sort of effective boson mass gets large and positive. You're in a paramagnetic phase. And here, there's another, again, sort of trivial fixed point at a very negative boson mass. You're in this sort of very deep Mexican hat potential. You have symmetry breaking. So these are phases. So there's sort of a putative sort of critical point there, but it's not a bona fide critical point because we would have to tune this interaction to 0, and that's fine tuning. Okay, so you could say this is a multi-critical point. It's not a bona fide quantum phase transition, which should have a single relevant operator, a symmetric operator. Okay. All right. So, but so if epsilon becomes 0 or negative, then that's a valid fixed point. That's the sort of Gaussian fixed point that describes 5-4 theory in 4 or higher dimensions. But we're interested in below 4 dimensions. So clearly we need to take this interaction seriously. We can't just assume, set it to 0. It's an important contribution. And so, it's a complicated non-Gaussian theory. What do we do? Well, what we'll do is as we'll see, we can do perturbation theory in a manner that is controlled as long as this epsilon parameter is taken as a small parameter. So we'll perform this path integral, and we'll compute these shifts in the coupling constants, but perturbatively in the interaction strength, and we'll see that this will be analogous to computing something in this perturbation theory in U in a sense, in epsilon rather. Okay, so we'll just use the linked cluster theorem or the Cumulin expansion. We're interested in the logarithm of a average of an exponential. Okay, this will be the shift, this contribution to the effective action for the slow fields. It's minus log of this average. Okay, so the linked cluster theorem tells you that the logarithm of this average is equal to the connected average plus some constant. Okay, so and then we can perform this average perturbatively because we can expand its exponential in powers of U. We compute things order by order in U. And at this point, it becomes clear that it's essentially an ordinary Feynman diagram expansion. Okay, so this connected thing. Okay, so I'll just sort of here. What I mean is that only connected Feynman diagrams appear. Okay, so what are the diagrammatic rules? Well, in the sense, there's sort of two sets of propagators. There's sort of external legs that will correspond to the slow field terms, and then we have single lines that will denote propagators, sort of fast field propagators. Okay, in case you can think you're integrating out fast fields and you sort of mediate interactions between the slow fields. So these are internal lines. Okay, so essentially to compute corrections to a given coupling, we just need to know how many external legs, how many slow fields we have in that term. That tells you how many external legs you have, and then you just compute all possible connected diagrams with that number of external legs up to a given order in the coupling. Okay, so schematically, what do we have? So we're interested in corrections, delta K and delta R. These are things that sit, inside the quadratic part of the action. So this is basically, computing corrections to the 2-point function of the slow fields. Okay, so the name of the game again. External legs are these fat lines, and then the thin lines are these fast fields. So there's one graph like this. So each of these vertices is a quartic vertex. So this is order U. And then we have other things, something like this. Okay, now this is 2-loop order. It's order, I'll say order U squared. And what you'll find is that, as usual, this perturbative expansion is also a loop expansion. That much is clear from standard perturbative quantum field theory. And so we're interested in these ones, and then we're also interested in delta U. So that's a correction to the 4-point function. Okay, so corrections to this will give us a delta U 4-point function, and okay, so we'll have things like this. So these corrections start at order U squared. Give essentially 3 graphs to consider. That order, all order. Okay, but there'll be higher order graphs like this, for example, 2-loop graphs and so on. Order U cube. Okay. So at this point, these are just diagrammatic calculations. I won't do any actual diagram computations for you. This can be found in many good textbooks. But essentially what you get, and at this point, it's useful we can even consider more general theory. We've talked about a single, one component by 4 theory appropriate to Ising, but we can consider an ON model with larger ON symmetry. So for a generic order parameter and component order parameter, then what you find are the following flow equations when you put everything together. Okay, so dr over dl, 2r plus n plus 2 over 6. There's various factors here. So powers of the cutoff, some integral of area of a d-dimensional sphere, which is various kinematical factors. K lambda squared plus r. Okay, so to first sort of to linear order in the couplings here, linear order in U, and then du dl, epsilon u minus n plus 8 s to the d lambda to the d u squared k lambda squared plus r squared order in U cube. Okay, this SD is 2 over 4 pi d over 2 gamma function d over 2. Okay, so those are the flow equations. So we now want to find. So they're not exact; they are valid to first non-trivial order in the interaction strength in U. So we want to solve them to find a fixed point, find a zero of these beta functions. And so the idea to do that systematically is called the Epsilon expansion. We want to treat this epsilon parameter, format as d, as a small parameter, and then expand, solve for this fixed point, these fixed point couplings, sort of order by order in powers of epsilon. Okay, so now we'll write r star is r naught plus r1 epsilon plus r2 epsilon squared, and then something similar for the U coupling. So we substitute this in there, we find the solution order by order. So it's clear from this equation that the U coupling there will be solution to order epsilon. That's non-trivial, and likewise for R. And so what we find is that besides the Gaussian fixed point Good. So I'm almost done here. Besides the Gaussian fixed point. Okay, yeah, and then we'll solve beta r star, u star, beta u, r star, u star to 0. Order by order. And so what we find is besides the Gaussian fixed point, we also find, Wilson and Fisher found a new non-trivial fixed point near 4 dimensions, u star 6. Okay, so again, this is found for any n equal to 1 or greater. Okay, again, as a power series in epsilon. In the one loop computation, you can only access the first term in this series, and then some other r star. Okay, so what does the flow look like? So we saw that the Gaussian fixed point was unstable in 2 directions, but that did not describe a bona fide quantum critical point. There's too many unstable directions. And so if we look at the flow computed at one loop with this interaction strength, so we still have the Gaussian fixed point there with these flows that take us away from it in both directions. But now what really happens is something like this. If I can draw this well enough. Okay, so there's a new fixed point, which is this Wilson-Fisher one. Get some value v and r, and the flows were taking us away from the Gaussian fixed point, and they basically take us away. They take us towards this new fixed point. Again, the flows look like this. So you see that the flows take you towards this new fixed point, and now this fixed point has only one unstable direction. Okay, so that is a valid candidate for only one unstable direction, a valid candidate for a quantum critical point. Okay, so is this the right fixed point? Well, at this point we need to compare. We need to compute exponents, compare with numerical simulations. Could be it, of course, Monte Carlo or Bootstrap, your favorite method. And again, we predict a whole family of critical theories for n, arbitrary n. And so okay, again, from this fixed point, we can plug in those values into our expressions for these anomalous dimensions and critical exponents. So likewise, we can compute these in powers of epsilon. Okay, so strictly speaking, this is a fixed point that is only exists near 4 dimensions, but at this point, the idea is to say, well, let's just be bold and extrapolate epsilon to 1, even though we only have a finite power series, and see if we get anything that's reasonable. Okay, so we could extrapolate, let's say, for to 1 for d equals 3, maybe even 2 for d equals 2, and see what we get. So yeah, so I don't have exponents for the d equals 2, but before I say that, let me just say that even though these critical couplings are kind of there's dependence on this bare coupling on these various coefficients, but the exponents themselves are so these fixed point values may not be universal. They may depend on your RG scheme, but these exponents are universal. Okay, so this is universal. Very nice. So we started from this very general idea that there should be scale invariance at the critical point, and we developed that into a fully systematic method to compute critical properties. Okay, so in the comparison, actually here, yes, I have just a few comparisons. For d equals 3 equals 2, we don't need this method. In d equals 3, we can ask what happens. So for d equals 3, so here I just looked at the correlation length exponent. So if we just sort of naively extrapolate, okay, so I'll look at 2 cases. N equals 1, that's Ising. So this would be for example, the classical 3D Ising model or the 2+1 dimensional quantum Ising model, transverse field Ising model. Or I could look at n equals 2. This would be the XY universality class. So this would be, again, classical XY model in 3 dimensions. Or, for example, the superfluid to bondage later transition in the Bose-Hubbard model at the particle whole symmetric point. So if you naively extrapolate, the one loop result. Oh, by that I mean, epsilon extrapolated to very naively. There's a very simple computation. For Ising, we get 0.583, and then if you look at the bootstrap value, this would be 0.63, and here for n equals 2, 0.6, and the bootstrap is 0.67. Okay, so with this one loop result, we don't get something that's amazingly close, but for something that's such a coarse estimate, it's not bad. And if we can do these computations to figure out higher orders. For example, for the ON model, I believe that orders are available up to 6 loop orders. So sort of epsilon 5. This can be resummed, and one can get very close agreement with these non-perturbative methods. Okay, so that's basically it. So I was going to say a few words about fermionic critical points, but I think it's better to just stop here. I just took this and I just plugged in epsilon. Yeah, that's right. So if you have a long, these are asymptotic series. So really, strictly speaking, even if you had, infinitely many terms, strictly speaking, they're not convergent series. So mathematically, it doesn't make sense to just plug in the number. And so, strictly speaking, you should first define some analytic continuation, some function that has, that's well defined, that has the same, sort of expansion up to a given order. And then once you've obtained that sort of resum function, that is analytic in some domain that includes epsilon equals 1, then plug in the value. So that you can do using various methods, so Padé resummations. There are sort of Padé-Borel resummations that are a little bit more involved, where you try to incorporate sort of more knowledge about what this series does. So there, for example, you may use, there are certain theorems that tell you about analytic properties of correlation functions or exponents in the limit of, at large orders in perturbation theory. So sort of that the coefficients of a perturbation series at large orders should have a certain dependence on the order. And you can use that to constrain sort of what the resummed series should look like. And so there's various sort of tricks to try to get a better behave function and then set in epsilon equals 1. So that's what naive is, sort of not doing any of this. You can do sort of more advanced things, but they're always a little bit ad hoc, right? Because there's sort of ways of defining a function that has this sort of series representation. They're not unique.
Should guarantee that you could always find a way to resum it such that it converges?
I don't know if you can guarantee, but in practice, of course, we don't have an infinite number of terms, right? So we only try to do things up to some order. So yes, practically speaking, up to a given order in perturbation theory, you can always write down a function. Okay, so the only potential problem is sometimes what happens is that you have some perturbative expansion up to 4th order, 5th order, and then you write down some Padé approximant, and then you find that this Padé actually will have some poles between, as a function of epsilon between 0 and 1. And then that means, there's an obstruction to continuing in dimension. So, that's not a valid Padé. You would sort of throw it out. In practice, you can often find these Padés. But yeah, at that point, it's sort of less rigorous. Right? But these expansions and their resummations have yielded quite good results, at least for these bosonic universality classes. Yeah, and also the theory is better controlled the larger the value of n as well. And then there's other methods like large n expansion, which is different.
Their symmetries and local equal to 3 the process
Right. Yeah. So that's right. So the d equals, right. So, that's the spirit of this expansion, right? So you need to remember that in the epsilon expansion, you're really formally working close to d equals 4, right? So the idea is that, you're close to d equals 4, so you throw away all the operators that are irrelevant, at tree level near d equals 4. And then, that's what allows you to systematically have an expansion in powers over epsilon, right? So you're not working directly in d equals 3. Otherwise, you don't have a well-defined expansion. So I agree with you that, phi 6 becomes marginal in 3 dimensions. But, and, there is, in the mean field theory, yes, it has some physical content in the sense that, if the coefficient of the u to the 4th term becomes, if it vanishes, then, there's a tricritical point, and then there's a first order transition. So there is also a tricritical Ising universality class. So if that's what you're trying to target, then that's right. That's kind of another question. But for sort of critical Ising, then the phi to the 6 operator does not play a role in this epsilon expansion near 4 dimensions. So you don't need to keep in the theory, even though you're continuing to d equals 3 at the end of the day. Yeah. So that's why, that's part of the method. Otherwise, yeah, there's often, sort of many more operators you would keep if you were not working near 4 dimensions. So that's why you have to work near 4 dimensions. Yeah, and if the theory is renormalizable, then you will only have finitely many, relevant and marginal couplings, or relevant couplings you need to keep. And yeah, relevant and marginal.
Are there examples where the epsilon expansion just fails compared to bootstrap or QMT?
Depends what you mean. So
this is pretty good. Maybe
you mean, yeah, that is it. Well, you always have to, yeah, there's different things, right? You could ask yourself whether the fixed point that you're, well, maybe, how can I say? It's not clear that a fixed point found near 4 dimensions always, becomes a valid fixed point in 3 dimensions, right? So, it can happen that this fixed point, for example, annihilates. If you treat dimension as a continuous parameter, right? You could have a situation where you have a fixed point near 4 dimensions, and then it could annihilate with another fixed point, as you go down in dimension before you hit d equals 3. And then, it's a fixed point that has no relevance to d equals 3 physics. So the example that we know, for example, these phi 4 models, these Gross-Levin models, we have good confidence that they're physical, for other reasons. For example, this theory, and the same can be said for the Gross-Levin models. You can study them, for finite n near 4 dimensions. You can also study them in fixed dimension in the large n expansion. And then you can check that the 2 expansions agree order by order in epsilon and 1/n. Yeah.
Is there a typo on the board?
There could be.
Because
where
you take n to be infinite for the new exponent.
Yes.
You put epsilon equal to 1, shouldn't that be
yeah, but okay, so what you would want to compute to compare with that is nu inverse, I think. Because this is sort of already, because there's going to be, you cannot just set epsilon equals 1 here, because these order epsilon squared terms will contribute as well. So you're trying to recover the result at nu equals 1 and infinite n, right? Well, depends what you mean. But so here, these terms in large n, they do contribute if epsilon is finite. So you can't just discard them. I don't have the expression here, but these corrections don't vanish. Like the theory does not become one loop exact in the large n limit in the sense of the epsilon expansion. And so you need to keep these other terms as well. But if you have the result for general d at the large n expansion, then what you can do is, suppose you have an exponent. The way to see the match is that you would take this result from the epsilon expansion to a given order in epsilon, expand this result to a given order in 1/n. Then you take, a large n result obtained in fixed d dimensions between 2 and 4, and as a power series, J, let's say, 1 to infinity, some coefficient J, and then, something like this, right? Yeah, because there's a contribution at 0th order. It's something like this. But this coefficient is a function of dimension. And so you can plug that in. You can set d equals 4 minus epsilon in there, expand that as a power series in epsilon. And for a given order in epsilon and over n, then the two series agree. Your order that's been computed, they agree order by order. So that tells us that, yeah, the fixed point, the theory, that we find in large n between d equals 2 and 4 is the same theory as this one. No problem. And also you can do 2 plus epsilon expansion from an ON sigma model, and you get the same agreement. So these checks have been done for these sort of classic, well-known theories. For more general theories, there's no guarantee that this always works. Yeah, and again, right, you could have this sort of annihilation. The fixed point disappears at some, I don't know, 3.2 dimension, and then it doesn't describe d equals 3 physics. So I would say I can't think of an example right now, but that's certainly possible, and that would be a failure of the epsilon expansion. Yeah,
I think random field Ising model critical dimensions. I think they don't really agree with the UMR. There's epsilon expansion results.
Yeah, for these random field theories, you can certainly do an epsilon expansion. Use this replica method. You do an epsilon expansion. Yeah, sometimes there are weird things happening. For example, for the random field Ising, the random mass Ising model, and the random field, I don't know, but you study this problem, and then the beta functions can have some pathologies. Like, for example, the series starts at order root epsilon instead of epsilon. And I think it's generally believed that it's a very, some things really, it's a poorly convergent series. You do find a fixed point. It probably is the right fixed point, but the series converges very slowly. The results are not in good agreement with numerical results. Yeah, I can't speak too much to that.
The random field model, they are in agreement. It happened a long time
Yeah.
ago.
Okay. That's very possible. Yeah. I see. Yeah, that's entirely possible. Yeah.
If you take the theory where you have a complex scalar and a Dirac fermion,
Yeah.
with a fermionic interaction, the Dirac theory has emergent supersymmetry.
Right.
If you remember, at some point in epsilon expansion, the unknown dimension of the phi Bosonic field operator is one loop exact.
Right. That's correct.
So if one loop you get the right answer, you expect from
In that case, that's correct.
if you
Yeah.
get higher orders, you get corrections.
No, that's right. That's quite nice. So if you calculate this naively, you don't know any supersymmetry. Right. So what William is, I was going to briefly talk about this, but I'll just sketch what happens. So you have a similar theory where, the Lagrangian is, you have a Dirac fermion, and you have, a complex scalar. There's again a mass term and a by 4 coupling. Okay, so again, there's a Wilson-Fisher type diagram with R and U. So you would find
Just maybe the coupling with
Yeah.
the
what's that?
boson term.
Yeah, I'm going to add that. I'm just sort of trying to be pedagogical, let's say. So, right, so there's a Gaussian fixed point. Again, it's unstable. Takes you away. You find a Wilson-Fisher fixed point, okay, here, something like this. This one is stable. Okay, so that would be the O2 Wilson-Fisher fixed point. But now in this theory, there's fermions that are coupled to this boson with a Yukawa coupling. Some sort of, it would be something like this in kind of spatter parlance. It's sort of a VCS interaction between an S-wave order parameter and some pairing field. Cooper pair fluctuations. And so there's a third axis here, which is this Yukawa coupling. And then what you find is that this O2 Wilson-Fisher fixed point is stable in the absence of Yukawa interactions, but it becomes unstable in the presence of this G. So this is unstable. And then in the end of the day, you flow to a new fixed point that, is stable in all directions except one, right? So it's stable in the plane of these interactions, and it has only one unstable direction, as you would expect for a critical point, and this fixed point has some emergent supersymmetry. Okay, so what you can do is you can calculate these anomalous dimensions, not knowing anything about supersymmetry. You would find that the anomalous dimension of the boson and the anomalous dimensions of the fermion, it's epsilon over 3, and that's it. There's no other corrections to that. And so when you set epsilon equals 1, you get 1/3, and that result is exact. It can be obtained by non-perturbative methods. On the other hand, so okay, so we've done this computation, to order, for loop order, and nothing happens. So it's same thing. But nu is very different. Nu has corrections and all that. Yeah.
So the story is that the diagrams cancel between fermions and bosons.
That's right. So there's some non-renormalization, right? So essentially, what happens is that the the only contribution to these couplings, to these anomalous dimensions are, yeah, that's right. So so this basically this coupling doesn't get renormalized. That's effectively what happens. So at the SUSY fixed point, remember that these two guys basically become the same. So there's some interaction. The fixed point values are such that these couplings are essentially the same, and then once you're there, then this coupling does not further renormalize. So essentially, this delta G is sort of 0, and that's a result that you can show using the SUSY formalism. So there's a non-renormalization of this superpotential. So all you have is sort of some one loop self-energy, something like this for the fermion, and then something like this for this. Okay, for the boson, this for the fermion, and then nothing else contributes. That's right. So I think what happens is that's correct. So there's some cancellation at higher order. There's some cancellation between these sort of pi4 diagrams and these fermion loop diagrams. And yeah, so that's a unique case where, because of supersymmetry, these things, the theory is one loop exact. That's correct. Yeah. Yes. Yeah. It's quite remarkable. That's right. Yeah, that's right. And also the fact that the SUSY occurs at all is quite unique.
We have to check this order by order for the boson and all dimensions.
Well, presumably this was some loop computation to finite order. So this, in a sense, was checked explicitly by explicit computation at for loop order. But it's not a mystery in the sense that you can prove this more generally using SUSY. This is sort of, if you didn't know anything about SUSY, that's what we find. Is there a diagrammatic proof? I think the proofs are sort of not perturbative using the superfield formalism. Presumably, you could give the same proof from a diagrammatic standpoint. This is just an explicit computation at a given order. It's not a proof, but it's consistent with what we expect from SUSY. Yeah, but that's only for these operators. So other operators, dimension, of phi squared, this is 1/2 plus something epsilon plus this doesn't terminate. So the dimension of these operators is not protected by supersymmetry. So there's some corrections. Yeah. Yes, question.
What happens if I put p equal 2 and then I want to get mu for xy?
Right. That's right. What happens if you? That's a good question.
Because mu shouldn't be well defined, right?
That's correct. Yeah. So in the form of the Epsilon expansion, yeah, that's a great question. I don't know the answer. You must get something that's just wrong. You just get a number, but it doesn't mean anything.
You get the number.
Yeah, because right. Like I wrote at one loop, I wrote down the expression, right? It's 1/2 plus a quarter. And you get a number, but it doesn't mean anything. Yeah, that's correct. Yeah, that's correct. So in other words, this theory does not have this Epsilon expansion below 4 dimensions or below the upper critical dimension does not know about the lower critical dimension. And that's the problem. So these expansions are really only valid, you know, if you're below these dimensions. Yeah. So here this is different now because we have a continuous symmetry. Yeah.
But maybe for eta would be better. For eta is fine.
Ah, right.
Like 1/4.
Yeah, that's right. It is 1/4. Yeah. So the eta in the phi-4 theory starts at 2 loop order. So the first term is order epsilon squared. The coefficient is relatively small because for this, yeah, it's like you get a small number. I think it's knowing the result for epsilon equals 1, which is like 0.0 something, and so it would be epsilon squared. So 4 times that. Yeah, maybe you get close to 1/4, but I guess it's just, yeah, it's a good question actually. That's interesting. Yeah, that's right. But yeah, this expansion doesn't know about the lower critical dimension.
So.
Okay, we'll stop here, right?
Again.
Thank you.
Well,